So, you think just memorizing P equals mv is enough to secure those top grades in your Cambridge IGCSE physics exam? Think again. Welcome to The Explainer. Today, we're completely dismantling that myth. We're going to look closely at momentum, impulse, and how the highest-scoring students actually approach these exact questions to guarantee top marks.
Listen, this is the exact painful mistake that thousands of learners make every single year. They walk into the exam hall, they see a momentum question, plug in the mass and the velocity, get a quick number, and confidently assume they've just bagged all the marks. But then results day rolls around, and they've lost critical points, sometimes dropping entire grade boundaries. So why does this happen? Because Cambridge examiners aren't just testing if you can multiply two numbers together. They're testing your deep application of scientific reasoning. They want to see your rigorous attention to detail and your ability to model reality mathematically.
Let's look right at why ordinary revision absolutely fails here. Take a look at this standard student response. Momentum is 10 kilogram meters per second. I mean, it sounds okay, right? It's got the correct units, it feels like a solid answer, but it is wrong. Now, contrast that with a top-tier elite answer. Momentum is negative 10 kilogram meters per second because it's in the opposite direction. That tiny little minus sign, that is literally the difference between an average grade and a top mark. It screams to the examiner that you truly understand the physical properties of what's happening, not just the basic arithmetic.
And the absolute crucial point is right here, treating it as a vector. A vector is a variable that has a magnitude, which is its size, and a direction. The Cambridge mark scheme rigidly demands you treat momentum as a vector quantity. Since we only need to look at motion in a straight line for this specific 0625 syllabus, velocity and momentum values in one direction are treated as positive, which means values in the exact opposite direction must be mathematically recorded as negative. If you miss this directional property, your entire calculation just cascades into failure, and those marks slip right through your fingers.
Okay, so how do we stop leaking these easy marks? We need a reliable system. Here's your first quick win. It's a simple 4-step framework to make sure you hit every single mark scheme requirement. Step 1 is the concept. You identify exactly what physics principle is at play before you even touch your calculator. Step 2 is evidence or data. This is where you carefully pull the exact numbers and units straight from the text or the diagram. Step 3 is scientific reasoning. Here's where you apply those tricky vector rules we just talked about, like assigning a negative direction. And finally, step 4 is examiner wording. You write out your final answer in the exact format with the right units and significant figures that Cambridge expects.
Now, in just a moment, I'm going to reveal the exact hidden examiner clue that flips the impulse calculation completely. It is a massive trap that so many students fall into. But first, you absolutely need the framework that makes that specific clue totally obvious. We got to make sure our foundation is rock solid before we tackle the hardest questions on the paper.
All right, there are 3 main equations where momentum features, and locking these into your memory is non-negotiable. First up, standard momentum, P equals mv. Second, the conservation of momentum for two objects, m1u1 plus m2u2 equals m1v1 plus m2v2. And third, impulse, Ft equals mv minus mu, which just means force times time equals mass times final velocity minus mass times initial velocity. Having these formulas memorized is obviously essential, but knowing how to actually deploy them under pressure, that's what gets you the A-star.
Let's escalate the stakes a bit and apply this framework to a real Cambridge-style scenario to test your visual reasoning. We've got a crane lifting some heavy steel girders. There's a concrete balancing weight of 10,000 newtons positioned at one end of the jib, exactly 5 meters from the pivot. On the other side, the steel girders are suspended 25 meters away from the pivot. Oh, and we're told to assume the jib itself has 0 mass. So, here is my challenge for you. Pause for a quick second and predict the correct examiner-style calculation for equilibrium. What is the maximum weight of girders the crane can lift at 25 meters? Remember step 1 of our framework, the concept. The concept here is the principle of moments, where the total clockwise moment must perfectly equal the total anti-clockwise moment to maintain perfect balance. How are you going to arrange the data using that exact principle? Let's walk through how this builds into the final answer. For the anti-clockwise moment, we take the 10,000 newtons and multiply it by its distance from the pivot, which is 5 meters. That gives us 50,000. Now, for the clockwise moment, we have our unknown weight multiplied by 25 meters. Setting them perfectly equal to each other, we simply divide 50,000 by 25. This proves that balancing the moments results in a maximum girder weight of exactly 2,000 newtons. Boom!
If you laid out that scientific reasoning clearly, actually stating the principle before jumping into the calculation, you've just secured full marks. Section 1. Harder example. Conservation of momentum. Let's really test that framework.
Okay, let's see how our four-step framework handles a much harder scenario. This is where the vector trap catches the vast majority of students completely off guard. We have two objects, Object 1 and Object 2, involved in a straight-line collision. Now, the fundamental rule here is that the total momentum before an event perfectly equals the total momentum after the event. But visualize the actual movement before the impact. Object 1 is moving to the right, and Object 2 is moving to the left. Because momentum is a vector, Object 2's initial velocity must absolutely be inputted into your calculator as a negative number.
To really lock in the scientific reasoning, look at the precise structure that Cambridge Mark Scheme actually wants to see from you. Before the collision, we use u to represent initial velocity, giving us the expression m1u1 plus m2u2. After the collision, we use v to represent final velocity, giving us m1v1 plus m2v2. Writing this equation out fully before you substitute any numbers in is your ultimate safety net. It proves to the examiner you understand the underlying concept of conservation, and it secures those precious method marks even if your final arithmetic goes a bit sideways later on.
Now, what if you face a practical question, something like Investigation 3.3 right out of the syllabus workbook, where two trolleys are involved in an explosion situation? You have to apply a very specific piece of logic here. In an explosion, two objects push apart from a completely stationary position. That means the initial momentum of the entire system is exactly zero. So logically, after the explosion, the momentum of one trolley moving left perfectly equals the negative momentum of the other moving right. The total system remains at zero.
Section 2. The clue revealed. Cracking impulse.
All right, the moment we've been waiting for is finally here. Cracking the impulse equations using that hidden examiner clue. There are two mathematically equivalent ways to think about and calculate impulse. You can either calculate the force on the object multiplied by the period of time over which it acts, which is F times t. Or alternatively, you can calculate the complete change in momentum of the object, which is mass times final velocity minus mass times initial velocity. You know, mv minus mu. Both are completely valid physics.
But here is the massive question that stumps so many students under pressure. How do you know which method the examiner actually wants you to use? I mean, both formulas work in theory, but usually the exact data provided in the exam paper only supports one path. If you try to force the wrong method, you'll end up with missing variables, you'll start to panic, and you will undoubtedly lose precious time and marks.
The answer to which method you need lies entirely in the specific command words and data clues strategically hidden in the question text. Spotting them is a learned skill, but ask yourself this: if you can master the math but still miss the examiner's subtle language, are you truly prepared for Paper 4? You can't rely on myths. You need a complete system to pull all of this together before exam day. To replace these common myths with a guaranteed strategy, it is absolutely mandatory that you watch our explainer on the ultimate last 7 days revision map right now. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Head over to the next explainer on your screen to get your 7-day revision map, keep practicing your vector directions, and I will see you over there.